Hi everyone, we're going to talk about support vector classifier today. This is the second part of the support vector machine lectures. So as a reminder, support vector machine is a family of algorithms for supervised training. They're not based on probability. It's a binary classifier. The base form is linear, although we will look at the nonlinear options as well. In the first lecture, we talked about maximal margin classifier, MMC. It's a hyperplane designed to maximize margins. The hyperplane is created using support vectors. It is very useful for separating two classes of data. However, it's also very sensitive to outliers, which is one of the main problems we're trying to solve using support vector classifier, which is the topic of today's lecture. So this is what we're going to focus on today, support vector classifier, which is an improvement upon maximal margin classifier. Maximal margin classifier, this is a recap from last lecture. This is the algorithm. Is designed to maximize the margin. M has to be greater than 0. It's a positive margin. When the margin is less than 0, that means we have failed to find a solution. So the classifier is actually this equation beta 0 plus beta 1, x1, beta 2, x2, all the way to the p feature. This equation is what we call a hyperplane. And to solve for this equation, we construct this algorithm as a convex optimization problem subject to a bunch of constraints. The solution has been implemented as library E1071 using the SVM function. So the SVM function can be used to solve linearly separable problems. The idea is that there are potentially many different lines that can divide this data set, and the maximal margin classifier is the line that is the farthest from both classes of data. The line or the hyperplane or the maximal margin classifier is this equation, beta 0 plus beta 1 x1 plus beta 2 x2. There are only two x's because there are only two x features used in this data set. So the equation is set to 0, and that is the MMC, and then anything that's to the left of the line are the green crosses. They're less than 0, and any dots that are greater than 0 are to the right of the line. So the maximal margin classifier or the hyperplane is determined by the support vectors or the borders of the two classes, which can be really sensitive to outliers. So if you draw this line, if you have these two classes that can be easily separated, what you can do is just find the borders, you measure the gap, and then you find the middle of the gap, and that's where you draw the hyperplane. However, if you have an outlier, which is this new green dot over here, if you have that outlier, that's going to force the MMC to be over here. Which is represented by the orange line. So that's a dramatic shift from the blue line to the orange line just to accommodate this one outlier. So the green cross over there is considered an outlier because it's actually close to the yellow class, the yellow dots, and it's far away from the other green crosses. So it's actually a misnomer or it's an outlier. It really doesn't belong in its own class. And this outlier kind of messes up the boundaries of the two classes. But if you just use the MMC trying to accommodate every dot, you're going to have this line that perfectly separates the two classes of training data, but it gives you a very small margin, which we don't really like. We want to be able to maximize the margins, want to have as much as possible in terms of M. And so when you're trying to accommodate this outlier, you're sacrificing your margins, which gives you a less reliable or less confident, less stable prediction model. Probably doesn't perform as well. So here's the illustration from the textbook. So you can see the blue dots and the pink dots. They can be perfectly separated by this hyperplane. However, if we add an outlier, which is this blue dot over here, the single outlier will dramatically shift the hyperplane from the dotted line to the solid line, which means that the model is not very stable. It probably wouldn't perform it very well, and the new model actually provides very thin margins, which means that the classifications can be a little shaky. So what we have talked about, what we have seen, is actually an example of the bias variance trade-off. In order to accommodate this outlier over here, we have a model that perfectly classifies the training data set. So it still separates the green crosses from the yellow dots perfectly, which means that it produces low bias at the training stage. However, if we are presented with a test data point, which is this white star, then this model, the blue line, is going to misclassify this testing data point, producing very high variance. We can also be presented with a data set like this. You can call this an outlier here, this green dot. You can say these are a bunch of outliers over here because these yellow dots are very far away from the rest of the yellow dots. But the reality is it's probably a data set that's impossible to be separated linearly. You can not easily find a single line that separates the two classes. So in this particular case, the MMC just wouldn't work. Here's another non-linearly separable problem that involves two x's, right? So we have x1 credit score, x2 mortgage amount, and then these two classes data. It's very difficult to find a line. Well, in fact, it's impossible to find a line that will perfectly separate the two classes. If we try to find an MMC, the algorithm will fail to produce a solution with an M that's greater than 0. So the algorithm fails. So to recap, we have presented a bunch of limitations of the maximal margin classifier. Number one, two classes are not necessarily separable linearly. So we may not be able to find a line that separates the two classes cleanly. Even when the classes are linearly separable, the hyperplane solution may not be optimal. It may be sensitive to outliers. A single outlier can dramatically alter the hyperplane, which leads to an overfitting problem that has low bias at the training stage, but high variance at the prediction stage. The model has tiny margins, which produces low confidence in the model. So the solution that we are going to present and explore in response to the MMC problems is what we call a support vector classifier. The support vector classifier uses a soft margin instead of a hard margin. What is a soft margin? The soft margin is the occasion where the margins can be violated by some training data points, meaning that it's okay to have some misclassifications or margin violations. In other words, these margins do not separate two classes perfectly, and that's okay. Misclassifications are allowed, which although we introduce more bias at the training stage, we produce a more robust model that is less sensitive to individual observations. So increases bias at the training stage, but hopefully gives us lower variance at the testing stage, which means better prediction. So with the soft margin, we're hoping to lower the chance of overfitting and get wider margins that give the model more confidence. So let's look at a support vector classifier. So these are our two classes of data along a single X feature credit score. Instead of trying to accommodate all the green crosses, what we do is we can find a soft margin classifier that classifies most of the points correctly with one exception. So there's one misclassification. So this classifier does not produce perfect performance at the training stage, meaning that this classifier produces higher bias than MMC. However, when we are presented with a test data value, this white star over here, this soft margin classifier will perform better by making a better prediction, which is lower variance from the MMC. Here is a support vector classifier. The solid line is the hyperplane. The dotted lines are the margins. And you can see this model actually has a bunch of data points in the margin, and there are actually some misclassifications as well. So let's take a look at them. On the margin, there are 3 dots that are right on the margin. There are also 2 values on the wrong side of the margin. So data point 8 is within the margin. The dots are supposed to be outside of the margins. But this one is within the margin, between the margin and the hyperplane. So that's called a margin violation. Data value 1 is also a margin violation. 11 and 12 are on the wrong side of the hyperplane. So 11 is supposed to be pink, and that should be in the lower side, but now it's on the upper side of the hyperplane, so it's on the completely wrong. It's called a misclassification because it's on the wrong side of the hyperplane, not just the margin, but the hyperplane. So you've crossed the line, which means that you have been classified into the incorrect class. 12 is the same thing. It's a misclassification. It's supposed to be blue, so it's supposed to be on the upper side, but now it's on the lower side. These soft margins allow classifications. The question is, how much do we allow? How much can we tolerate misclassification? Do we allow a lot, or are we very strict and we only allow a handful? In order to do that, to determine how much we can tolerate this, we can actually use the tuning parameter C. C stands for cost. This tuning parameter specifies the allowance for misclassifications. When the tuning parameter C is 0, that means we have 0 tolerance for misclassification. So we do not allow misclassifications or margin violations at all. That C equals 0 when we have a maximal margin classifier. However, when we start to increase C, when we start to use a positive value for C, then that means we're allowing some tolerance for margin violations and misclassifications. C is the budget that we have for slack variables. Slack variables are noted as epsilons. So every data value is given a slack variable, epsilon. Epsilon allows the data point to be misclassified. So when the data points are on the margin, the epsilon is 0. Margin violations, epsilon is greater than 0, so epsilon measures the distance from the data point to the margin. When you have a misclassification, that means you've crossed the line because the margins are sort of standardized to be -1 and 1. So when epsilon, when the data point crosses the hyperplane, that means you have an epsilon that's greater than 1. These epsilon values, there's an epsilon value for every data point, and you can add them up, and that is the sum of the epsilons indicates the total amount of slack. And C controls how much slack we're willing to allow. So if you have a big C, that means you allow a big budget for slack. If you have a small C value, that means you are not willing to allow a lot of slack. Okay, so slack is epsilon is really just the amount of lenience or deviations you allow the data point to be away from the margin. So in this particular case, we can consider C to be a penalty term. In our previous machine learning lectures, we have talked about penalty a lot. So penalty is really a term for sacrificing training performance in order to gain some testing performance. So what we do is we penalize training performance, hoping that we'll be able to have a better prediction model. C, the penalty term, again, indicates the maximum allowance for margin violations and misclassifications. And because epsilon is greater than 1 for misclassifications, C will allow no more than C number of misclassifications. Recall that support vectors are the points that determine the classifier or the hyperplane. They are, in this particular case, when we have the soft margins, support vectors are those that are on the margin or violates the margin. So if we look at this data point, this data set with the soft margins, you will see a bunch of violations. So this one, this one, this one, this cross over here, it's on the margin. This one is also on the margin. This one is a violation. Well, it's not a violation. This one is a misclassification, so it's completely on the wrong side. So when it's a misclassification, that's also a support vector. So in this particular case, we have a total of 6 support vectors that are used to calculate the margins. The yellow dots and the remaining yellow dots and remaining green crosses are completely outside the margin. So they are classified correctly. They have 0 influence on how the classifier is constructed. So let's look at the behavior of C. When C goes up, which means we're more tolerant of errors, misclassifications, and margin violations, that means we're allowing a lot of slack. So the sum of epsilons will go up. And because we are more tolerant, we actually get wider margins. So M will go up, and we'll also get more support vectors. When C goes down, the total amount of slack will go down. That means we're less tolerant. We'll get a narrower margin. M will become smaller, which also means that when you have smaller margins, you include fewer support vectors. In a sense, the tuning parameter C performs the role of regularization, which is what we talked about when we talked about lasso and ridge regression. Those algorithms regularizes linear regression models. Regularize moderates the beta coefficients. In this particular case, C performs a similar function. it regularizes the trade-offs between training and testing, right? So C sort of controls how lenient or how strict we are in terms of how many errors we're allowing. So you can actually pick a C value that's very small. That means you're very strict about misclassifications. You get narrow margins, you get fewer support vectors. In this particular case, you will be able to minimize the training bias, so you get better training performance, but usually that means you get more variance for testing. You can also get a bigger C, sort of a bigger budget or allowance for slack. That means you're more lenient about misclassifications. You will produce a wider margin that uses more support vectors to construct the classifier. When you use more support vectors, you get more confidence in the model, and the model becomes more robust and more reliable because you're using more numbers to calculate. So usually that would, because you allow more misclassifications, your training performance will suffer, which means higher bias. But usually we do that with the hope to reduce the variance. You don't always reduce the variance, but you tend to get that. So what you do is you would do cross-validation, you vary the size of C, tune it from left to right, from small to big, and you have to find the optimal C value that gives you the best balance between bias and variance. Here I want you to take a look at the SVM function in R. The way it is defined, there is a parameter called cost. Cost is the parameter that is equivalent to C. However, it's very important to remember that cost is actually inversely related to C, meaning that a big cost value actually means a small budget for tolerance or slack. So when you have a big cost value, that means you have a very small C. Whereas when you have a small cost value, that means you're more lenient, you actually get a wider margin and more support vectors. So smaller cost means bigger C. Bigger cost means smaller C. This is a little tricky, so I want to make sure that you're aware of this very particular design of the SVM function in R. So using the SVM function, you will be able to figure out the hyperplane, which is the equation for the support vector classifier. That would be the blue equation in the middle, beta 0 plus beta 1, x1 plus beta 2, x2 equals 0. So anything above 0 is on the right-hand side. Anything below 0 is on the left-hand side. 1 and -1 are the size, the standardized size of the margin. So once you have constructed the SVM model, you can actually use the COEF or COEF function to request for values of beta 0, beta 1, and beta 2. Once you have these values, you can actually construct the hyperplane equation. So here is how support vector classifier works. We will have a data frame that has x1, x2, and the actual y values, the classes. And then we can run the support vector classifier using these three columns, x1, x2, and y. You'll be able to come up with an equation, beta 0 plus beta 1, x1, plus beta 2, x2. And then using the optimized SVC equation, this hyperplane, you can actually calculate. You will just plug in the beta 0, beta 1, beta 2, the coefficients, and also the x1 value and x2 value to be able to calculate your fitted y hat. The fitted y hat will be these values. They are not between 0 and 1. These are not probability values. These are just actual values that you get by plugging in the numbers. So you get some negative numbers and you get some positive numbers. The way support vector machine classifiers work is basically looking at these numbers and say anything that's less than 0 will be put in the -1 class. Anything that's above 0 will be put into the +1 class. You will see the y hat classification. Now we have 2 green crosses and 4 yellow dots. So that's our predicted values. The decision value is basically what y hat is. So y hat is called a decision value in R, in the SVM model in R. So when the decision value, which is the fitted y value, is less than 0, then we assign the class label of -1. When the decision value is greater than 0, we assign the class label of 1, and this is how class predictions are made. Once we have the predictions, then we can look at how well we have performed with the predictions. These are correct predictions. So the actual y's are crosses, and we actually predicted crosses. So these are true negatives. This is a false positive, so this is a misclassification. The actual y is a green cross, but the y hat class is actually a dot. So this is misclassified. A negative is misclassified as a false positive. These are positives, and they're actually correctly classified as positive. So these are true positives. So we can take these counts and turn that into a confusion matrix. So we have 2 true negatives, 1 false positive, 0 false negative, and 3 true positives. With this confusion matrix, then we can calculate the specificity and sensitivity values of this model. And that's it. So here I want to summarize main functionalities of the SVM command in R from the library E1071. So you can see that SVM is actually pretty straightforward. It takes the formula format y tilde x. You specify the data frame. So far, we've been using the linear kernel because we've been building a linear classifier. So you would just say kernel equal linear. The cost is an inverse value of C. So when you have a big cost value, that means you have a very small C budget, and vice versa. Scale means that you normalize the X values because you can see that SVM models are constructed using geometry, Euclidean distances, optimization mathematics. It's very sensitive to scale. So you definitely want to normalize your X values before you run SVM. You can get a summary report of the model using the summary command. You can see a list of support vectors by using $index subcommand on the model. You can also list the beta coefficients using coef. We've seen this before. You can also get your class predictions using the predict function. Finally, you can get a list of fitted y hat values by using attributes of the predicted model. You have to say decision.values equal true. That way the prediction model will produce the fitted values rather than the class predictions. And then you use the attributes function to access $decision.values. On the right-hand side, to cross-validate and choose models, you can use the command tune. Tune takes an SVM model, the y tilde x formula, And then you can give it a range of cost values. And tune would you look at run models using 3 levels of cost settings, and it'll tell you which one is the best model. You can access the best model using $best.model. You can also plot the SVM model. This plot function will very conveniently plot all the support vectors as crosses. Here's the summary report of the SVM model. You can see the formula. You can see that it's a classification model using the linear kernel with the cost setting of 10. It tells you there are 7 support vectors. 4 belong in the -1 class and 3 belong in the 1 class. The output is 2 classes. This classifier makes 2 class predictions, -1 versus +1. You can also use the coefficients to construct the SVC hyperplan. So with the coef command, you can access the intercept beta 0, beta 1, and beta 2. And using these numbers, you can construct the equation for the hyperplane and also for the margins. And then you can plug in the numbers to make a prediction of y hat fitted value. And that's it. This is how we construct and support vector classifier.